All right, this is our first regression problem. So 2018 question 1, the manager of a grocery store selected a random sample of 11 customers to investigate the relationship between the number of customers in the checkout line and the time to finish checkout. I'm going to write down N as 11 because I might need that. As soon as a selected customer entered the end of a checkout line, data were collected on the number of customers in line who were in front of the selected customer and the time in seconds until the selected customer was finished with the checkout. The data are shown in the following scatter plot, along with the corresponding least squares regression line and computer output. Identify and interpret in context the estimate of the intercept for the least squares regression line. Well, please remember, that's my y-intercept row. This is my slope row. And customers in line is X. This is my y-intercept. And that's my slope. So 72.95 is the predicted amount of time in seconds that it would take to complete a checkout if there were 0 customers ahead of you in the line. All right. So that's what we expect. We expect to take 72.95 seconds if no one's ahead of you. Identify and interpret the context, the coefficient of determination. We never use this, so it'll be this. So 73.3% of the variation in checkout time can be explained by changes in the number of customers in line. All right, because this is the X. And checkout time is our Y. One of the data points was determined to be an outline. Circle the point on the scatter plot and explain why it's considered an outlier. All right, that's my outlier. Why? Is because it's significantly below where it's supposed to be. Because the observed checkout time is significantly less than the amount of time predicted relative to the other data points. All right? When there were 3 customers in line. So when there were 3 customers in line, I was expecting to be up here somewhere. This is where I was predicting it to be on this line right about here, but we're way down here. So these customers got out really, really fast. That was a really fast checker. So this took a lot less time. And by the way, since it's below the line, this would have been a negative residual. All right. It looks like I would have been expecting about 500, maybe 550 seconds, and I'm well under that. Okay, so very, very fast checkout for that person. All right. Okay, let's go ahead, and even though that this is the next one, even though it's a new problem, that was so short, let's go ahead and continue. So this is 2022, and it says based on a scatter plot, and so we have a biologist who gathered data on length in millimeters and mass in grams for 11 bullfrogs. So our sample size is 11, and that might prove to be important. Based on a scatter plot, describe the relationship between mass and length in context. Well, I'm looking at it, and I was like, okay, reasonably linear, definitely positive. The data points are pretty close to the line, so I'm going to say it's a strong positive linear relationship. So there appears to be a strong positive linear relationship, and I have to always have the context between bullfrog length and bullfrog mass. From the data, the biologist calculated the least squares regression line for predicted mass from the length. Identify and interpret the slope. Well, here's our slope. And I always put it over 1. So 6.086 grams over 1 millimeter length. So, because that's my X, so it's going to the denominator. Length, millimeters, grams up top. So on average, we would expect a 6.086 increase in bullfrog mass for every 1 millimeter increase in bullfrog length. Or for every 1 millimeter in bullfrog length, we would expect a 6.086 gram mass increase in mass for the bullfrog. Interpret the coefficient of determination of the least squares regression line, and they're telling us is 0.089. Okay, 81.9% of the variation in Y, bullfrog mass, can be explained by changes in the X of the bullfrog. Make sure it's always in context. Make sure you always write it like that. Based on the plot, approximately what length of mass a bullfrog will have the largest absolute value. So they're saying absolute value residual. So that means farthest from the line. It could be way above or could be way below. Well, that's my point. And I'm just going to estimate that that's 162. Now, maybe you get 164, 165, 163, something like that. You'll be fine. So 162 is the length of bullfrog with largest residual, and the mass is 355. Here's the problem. This said length and mass. Don't forget to have them both. All right. Well, how did I get the maths? I kind of drew a line over here and I said, maybe there. It's going to be close. All right. Does the least squares regression line overestimate or underestimate the line? I mean, overestimate or underestimate the bullfrog in this part. Well, they're below the line, so I have a negative residual. So definitely overestimates. All right. So the regression line overestimates the mass of the bullfrog. The regression line predicts, and here's what I did. I said, no, they gave me a regression equation. There it is. And I put in 162. I just plugged it in. And I said, oh, they predict it to be 440. Well, I see that it's about 355. So the regression line overestimates the mass of the bullfrog. The regression line predicts that the bullfrog with a length of 162 would have a mass of 440, and this bullfrog has a mass of 355, which is much less than predicted. The next thing was not a question that they asked, but I put it there, is calculate the value of the residual. Well, remember, residual equals observed minus expected. Well, we observed it to be 355. I plugged into the equation and got 450. So I ended up getting a negative residual. And guess what? Negative means it's below the line. Sure enough, we're below the line, and we overestimated the mass of that bullfrog. All right, that bullfrog's mass was overestimated. All right, this concludes statistical inferences.